Hmm. Welcome back, everybody. In this video, we'll be working on the second half of section 6.4. So we were working on the central limit theorem. So I wanted to start with one more example. In this one is about gondola safety. It says a ski gondola in Vail, Colorado carries skiers to the top of a mountain. There's a plaque stating that the maximum capacity is 12 people or 2,004 pounds. That capacity will be exceeded if 12 people have weights with a mean greater than 167 pounds. Because men tend to weigh more than women, a worst case scenario involves 12 passengers who are all men. Assume that weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. In part A, it says find the probability that if an individual, so this is about one, if an individual man is selected, his weight will be greater than 167 pounds. So again, as always, I would start with a little sketch. Let's do that down here. There we go. So we wanted to know the probability of being greater than 167 pounds. So the mean is 182.9 pounds. And we're looking to be greater than 167 pounds. So what we'll need to do is find the corresponding Z for 167 pounds. The standard deviation is 40.8 pounds. So we'll calculate. Get negative 0.39. Okay. Looking up 0.39 in our Z table, negative 0.39 will have 0.3483. That's for the area to the left of negative 0.39. And then again, as always, we want the area to the right of that. We'll need to subtract from 1. And so we'll get 0.6517. So there's around a 65% chance that one individual will be have a weight that is greater than 167 pounds. In part B, we're to find the probability that 12 randomly selected men will have a mean that is greater than 167 pounds. That would make it so that their total weight is greater than the gondola's maximum capacity of 2,004 pounds. So in part B, we're looking at a similar situation in terms of the picture. In part A only, we're looking at a group of 12 people. So that affects how we calculate the Z-score. We are comparing our sample mean, the mean of those 12, against the mean of the sample means. And then we have the standard deviation of the sample means below. So that will be 167 minus 182.9. And then down below, we won't just have 40.8. We need to divide by the square root of the sample size. It's 12 men, so we'll have the square root of 12 in the bottom. So we need to be careful how we type this in. Looks like negative 1.35. Okay, so then we'll need the probability that Z is less than negative 1.35. Once again, looking to our z table, 0.0885. We still want the area to the right, so we'll again take the complement of that. That's 0.9115. All right, so what does that say? What that says is that if we take a group of 12 men, the probability that they will have an average weight that is more than 167 pounds, that probability is a little over 91% chance. So that helps us answer part C. Does the gondola appear to have the correct weight limit? I would say no. It should be lower, because as is, it's relatively easy, in a sense, for the capacity to be exceeded. Okay. All right, so we're starting there with one additional example. In the next part, we are going to take a look at what's called the finite population correction factor. And what this is about is the following. In the central limit theorem, we use sigma over the square root of n. When we do that, we're assuming the population has infinitely many members. If we're sampling with replacement, that is putting back each selected item before making the next selection, it's as if the population is infinite, even if it really isn't. If you think about it, if you have a jar with 10 marbles of different colors, if you're reaching in and pulling out marbles and noting their color, and if you put the marble back before drawing the second marble, you basically have a infinite supply of marbles. So with replacement, it acts as if there's an infinitely sized population. In reality, a lot of times we do sampling without replacement, so successive samples depend on previous outcomes. In manufacturing, quality control inspectors will sample items from a finite production run without putting them back. We've used this example before. You're not going to crash a car and then put it back and have it potentially be reselected, right? So depending on the size of the population, we may need to use what's called a finite population correction factor. So if the sample size n is greater than 5% of the population size, that's a capital N. So now we have two different n's. Little n is the size of the sample, capital N is the size of the population. If you're sampling more than 5% of the population, that is little n is bigger than 0.05 times big N, we need to adjust that sigma x bar by multiplying by this factor. The factor is shown here in underneath this square root, in the middle of your screen. So that is the finite population correction factor. So let's break that down a bit. Underneath the square root, you have a fraction, big N minus little n. So the population minus the sample size, and that's divided by 1 less than the population size. Notice that if the sample size is relatively small, that is, and little n is small, then big N minus little n is pretty close to big N. For example, it's always easier with a concrete number. If let's just say that big N was 1,000 and little n was 5, okay, then big N minus little n is 995, and that's pretty close to 1,000, right? But if little n is not so small, right, let's say that little n is 320 and big N is 1,000. Now big N minus little n is not so close to big N, right? If little n is small relative to the size of the population, then big N minus little n will be pretty close to big N. So for problems like we've been working on up till now, up to including the gondola problem we did previously, The sigma sub x bar, which is sigma over the square root of n that we've had before, we'll be multiplying it by this square root, the square root of big N minus little n over little n, big N minus 1 rather. So best way to see how this all goes is to try it. So we're going to try it right here. So let's take a look. So here it says, in a study of babies born with low birth weights, 275 children were given IQ tests at age 8, and their scores approximated a normal distribution, and then the mean and standard deviation are given along with the source. 50 of those children are to be randomly selected for a follow-up study. Maybe we want to see, okay, how do these kids go on to perform in high school after they've been given this IQ test at age 8? So we're going to select 50 of those 275 kids for a follow-up study. In part A, it says, when considering the distribution of the mean IQ scores for the samples of 50 children, we want to know if sigma x bar should be corrected by using the finite population correction factor. Yes, why or why not? And then what would that value of sigma x bar be? So I think it should be yes. And then to see that, notice that the size of the sample we're taking a sample of 50 kids, right, out of the population of 275. 50 out of 275 is about 18%, which is bigger than 5%. So yeah, we need to use that finite population correction factor. In order to really see that, you need to make sure you've got the right population in mind. We're not studying all kids, okay? The population here is the 275 kids who were given the IQ tests at age 8. The sample that is taken is the 50 out of the 275. The population is not all children. The population in this problem is 275 kids. So it's 50 out of 275, and that's 18%, just about, which is a little bit bigger than 5%. So we do need to use that correction factor. So then our sigma x bar will be sigma over the square root of n times that square root, big N minus little n, over big N minus 1. So let's fill in our particular values. So the sigma was 16. The square root of n here is our 50. That's little n, right? And then square root, big N, that's 275, minus little n, that's 50, divided by big N minus 1. Okay, let me pause while I calculate that. So after going through the calculations, that standard deviation ended up being 2.05 with that correction factor in it. So now we want to find the probability that the mean IQ score of that sample of 50 kids is between 95 and 105. So I've already started with a picture in here. Those are our X values. We're going to have to calculate some Z scores, look up some values in the table. So let's start with 105 first. So Z will be X bar minus mu X bar over sigma X bar. And that denominator, fortunately, we calculated a minute ago. So we'll have 105 minus 95.5 divided by our 2.05. Okay, and I'll calculate that in a minute. And then we need to do the same thing for 95. Z will be X bar minus mu X bar over sigma X. Now we're doing the left end. It's 95 minus 95.5 divided by 2.05. Okay, so let me calculate that for you. All right, so we worked out to get for 105, the Z-score is really large at 4.63. And then for 95, it's negative 0.24. For 4.63, the probability that z will be less than 4.63, that value is not going to be in your z table. It's just too large. Our z table goes up to like 3.9 or so. And there the area is virtually 1. So we're just going to go ahead and use 1 for that. It's not exactly 1, but it is so close that we round off to 1. For negative 0.24, that one we'll be able to find. For negative 0.24, we'll get 0.4052. Okay, and so if we want that red strip shown in the picture, it's going to be the difference of those two areas. So the probability that z will be between negative 0.24 and 4.63, which is what we wanted, is that 1 minus 0.4052. 0.5948. So we have one more example. So the story here, it says the amount of time that a bank teller spends with each customer is normally distributed with a mean of 3.1 minutes and a standard deviation of 0.4 minutes. In part A, it says a random sample of 40 customers is taken without replacement from a population of 500. We want the probability that the average time spent per customer will be at least 3 minutes. For comparison's sake, we'll make the calculation both with and without that finite population correction factor. So either way, I'm going to start with a picture. So we will have the mean, which is 3.1 minutes. And we wanted to compare to 3 minutes. Okay, so we're going to do this without the correction factor first. Okay, so we'll have z-score. Z will be the x bar minus the mean of the x bars over sigma over the square root of n. So for this one, we want our sample to have a mean of at least 3 minutes compared to the 3.1 mean of the sample means. Our standard deviation, 0.4 minutes. Our sample size is 40. So let's go ahead and calculate that. So negative 1.58. Probability that z will be less than negative 1.58 0.0571. We wanted the right tail for this though, so we'll take 1 minus 0.0571. Okay, get 0.9429. Okay, that's without the correction factor. What would suggest to us that we actually need the correction factor is the fact that 40 out of 500 is 0.08, and that's bigger than 0.05. So since our sample size is more than 5% of the population, we will need to do that correction factor. So the same picture, different z-score though, as we'll see. So we'll have 3 minus 3.1 still. Our denominator is going to be more complicated this time. 0.4 over square root of 40. That part's the same. What's new is that big square root. It was big N in the top of the fraction. There was big N, which is our population. That's 500. And our sample size was 40. Down below, it's big N minus 1. Okay, so let me calculate that and then get the z-score. All right, so going through the calculations, our z-score with the correction factor in it ended up being negative 1.64. You have to be very careful how you type in this calculation in your calculator. Of course, you know, a lot of this you can do in your head, but be very careful how you type it. Negative 1.64. Looking at our negative z table, that gives us 0.0505 is the area to the left. And so, of course, we want the area to the right, which is 0.9495. So we can see that that's pretty close, but not the same on these two. Now we're going to redo this whole problem basically, but with a sample size of 15 instead of 40. So we just want to compare that and see how that is different. So we'll start, we can use the same picture. So let's go ahead and use the same picture. And as before, we went the area to the right. So as before, we'll start with without the correction. And so this is going to be almost the same. We just need to change that 40 into a 15. And of course, we'll get a different z-score. That's negative 0.97. So then looking to our table, 0.166 for the area. And then we wanted the area to the right. That's 0.834. Okay. Then we'll try it with the correction. So that'll look really similar to what we have above, only, again, our 40s will now need to be 15s. Again, let me calculate the z-score and give you the probability for that. All right, so going through the calculation with the correction, we ended up with negative 0.98 for our z-score. Looking up that value in the standard normal table, we get a probability of 0.1635 for the area to the left. To get the area to the right, as always, we'll subtract from 1. This gives us 0.8365 for our final answer. So these are a couple of examples illustrating that finite population correction factor. And it's, to summarize, basically an adjustment that we need to make when we are sampling from a population and the size of our sample is more than 5% of the size of our population. And it's to account for the fact that we're not sampling from an infinite population. All right, so that takes us to the end of this section. If you have any questions on it, let me know, and have a great day.